and we'll then go to the technical presentations. So it will let some times to people to join us. We will now shut down all the mics and cameras, and you will be able to react and comment through the chat. So CARIB-COAST, okay. CARIB-COAST project for Caribbean network for the prevention of coastal risk related with climate change is an ongoing project led by the French Geological Survey and funded by the European Interreg Caribbean program. So the overall objective of the project is to pool, co-build and disseminate knowledge and surveillance approaches, coastal risk and adaptation to climate change in the Caribbean. And as you can see, we are now in the last months of the project that is ending in December 2022. So we have a consortium of 11 partners, French research institutes, IFREMER, the National Forestry Office, the Institute for Research and Development, CARIB-COAST, that is the Marine Protected Areas Centers in the Caribbean, national research centers, and we also have extra European partners, University of the West Indies in Trinidad, Institute of Marine Affairs of Trinidad, CARIB-COAST in Puerto Rico, MONAGIS in Jamaica, as well as the Association of Caribbean States that provide us with a larger Caribbean network. The project also have the support of local agencies, the region Guadeloupe, the state services in Martinique, and the water offices in Martinique and Guadeloupe. So the project is divided in 3 technical components. Observation and modeling of present day and future hydrodynamics. This is the topic of the workshop today. Monitoring and mitigation of coastal erosion, and decision support tools. So the first component addresses the hydrodynamics in the Caribbean from the larger spatial and temporal scale, Caribbean circulation and future climates, through the local assessments of present day and future coastal hazards induced by hurricanes and tsunamis. The second component of the project is the monitoring and mitigation of coastal erosion. This includes networking of monitoring activities, as well as experimentation of ecosystem-based solutions. And the last part of the project aims to develop decision support tools for risk management and adaptation through the capitalization and disseminations of good practices, operational tools, as the storm monitoring network that was developed, and various training and awareness sections, including technical workshops as today, public conferences, and field visits with the local stakeholders. So the purpose of the workshop today is to present the activities undertaken within this first component on hydrodynamics and modeling activities. We will have 6 presentations by the team involved in these components: coastal hazards, ocean modeling, coastal circulation modeling, as well as several examples on activities undertaken in Trinidad, Jamaica, and Puerto Rico, and the Virgin Islands, US Virgin Islands. A last word before we begin. Okay. All the results you will see in the presentations today will be freely accessible, available within a few weeks through the CARIB-COAST websites, including a visualization platform that will allow to have all the modeling results on present day and future ocean and climate modeling, and hurricanes time series, hurricane simulations, and tsunami simulations. So everything will be available in the project is ending in a few months, and we expect to have this available in a few weeks on the website. So that's all from me. I hope you will enjoy this webinar, and I will let Andrea and Rodrigo begin with the first talk on coastal hazard modeling. Thank you.
Thank you, Jan. I share my laptop. Our presentation is okay for you?
Yes.
Okay. Okay. The presentation concerns coastal flood assessment at BRGM, of course, with a focus on the Caribbean. We present 2 persons, with Mian and with Andrea. And this talk concerns the work of Jeremy Romer from statistics, and one from seismic, tsunami, Lugar Paya from numerical modeling, and Rémi Tréblement from climatology and cyclones. Just a few words about coastal activities at BRGM. We are 40 permanent persons working on coastal topics. It's a multidisciplinary team with geomorphologists, sedimentologists, geologists, of course, oceanography, graphers, physicians, fluid mechanics. We have 3 to 4, 5 PhD students per year and 2 to 4 postdocs per year. These 40 persons are in regional office, like Guadeloupe and Martinique, and in a coastal risk and climate change unit. For now in Orleans, but they move in next years in Bordeaux. The main topic that we deal is concern coastal dynamics, coastal erosion, coastal flooding, and the climate change effects. This is for event like here, like tsunamis or cyclones, to long-term scale, like sea level rise impact. How to BRGM contribute to tackle it? Thank you to a partnership, because we are here in the center of on coastal risk, hazard and risk, and we collaborate a lot with a lot of specialists in biodiversity, maths, physics, numerical methods, meteorology, climatology, geography, and socioeconomy. This concerns national institutes, academic research teams, and private companies. This through different projects and national to international projects like CARIB-COAST, and to thanks to our internal dynamics between research and support public policy, thanks to our regional agencies. What is our approach on coastal flooding? Here in BRGM is multidisciplinary and multi-scale. We can deal to global to local scale, global for tsunami or for example, and we deal with geological expertise, historical documentation, data acquisition, feedback analysis after major events, like the last hurricane is concerned the Caribbean area. We can realize databases like in CARIB-COAST project. We can produce extreme analysis for 1, 2, or 3 or more variables. We take into account the uncertainties. We work a lot of modeling, wave water level, current flooding. You can see this with the presentation of Andrea, and with meta modeling or sub-brigade modeling to increase the number of model results is necessary for uncertainties and for example, this is we deal too with the impact at the cost, at the purse of the building, the damages, in a climate change environment. And the societal issues are historical here concern the prevention, but we were working more in adaptation, forecast, and crisis management, even on long-term scale, and coastal hazard due to storm, hurricanes, and tsunami. Now we, of course, work on CARIB-COAST project. What is our approach, modeling approach, that is concerned for storm, tsunami, and hurricanes? Here you have the phase of generation and propagation with the main models that we use for hydrodynamic, tide and surge. We deal with CARIB-COAST, it's a fresh version of Rom's model, and we develop also our model. Andrea can present you this new model, WINA. And for wave, we work a lot with Wave 3 model and WINA, and for tsunami, of course, we work a lot in the generation of the seismic tsunami, and for the propagation, we use to WINA. And For the flooding, we use nesting and coupling with other models. These are research model, French research model. Other ones, you know, is an international model like SWAT from Wave is a French model that we modify for the flooding, and of course the WINA one. And for this, we can take into account the impact of the climate change via sea level rise or the mitigation of the wave or storm surge. Okay, of course, a key point for us is the model validation or calibration. We collect a lot of as possible data, like from spatial satellites. Here you have a comparison between tracks that the track that you have here on the point are the significant wave heights, and is the model. When you don't have anything, it's very useful. Of course, we work with buoys and data caches for events. This is a depth inundation after a tsunami here. First, and you can see the in situ observation and laboratory. That's okay. The last two images. And now, Andrea,
okay, so hello to everybody. Now I will present to you our activity inside the CARIB-COAST project. So this was more of, on two main axes. So once was in order to provide an evaluation of cyclone-induced water levels and waves using a probabilistic approach in order to evaluate 100-year return period on present day and future climate. And the other one were more focused on simulating coastal water levels and time delay for tsunamis by using a deterministic approach with the hypothesis of worst credible case. So in the presentation of today, you will see from the generation to the propagation of the large-scale modeling. Since the simulation on flooding it's an ongoing work, so you will just see some examples at the very end of this presentation, but on other sites. So now concerning our probabilistic approach on hurricanes, if one want to apply this approach, of course, he has to deal with two major problems. The first one is the data which are available. There are only few historical data, and that's why, in order to have a robust probabilistic analysis, we need to go to search for some synthetic track database that have been very recently produced, especially for future climate. So here I cited the STORM database, which we actually used in this project, but some others are available. Or a third way that we tested inside this project, but we didn't finalize, could be to develop an in-house tracking and detection strategy based on some JCM projection, climate projection. So you can see an example in the pictures on the right. This consists in following detected areas that are displayed in yellow day by day, that are cyclogenic areas, and follow their propagation, their evolution in the domain, in order to be able to identify a possible track. So, as I said, finally we abandoned this approach, and we used simply we took our database from our cyclones from an existing database. The second problem one has to deal with is how many cyclones to be included for producing the statistical result. Existing method in literature uses thousands of cyclones, and we would like to overcome this need. So we worked a lot on this problem, and finally we published a very recent approach, which is called the STM-E approach, which actually allows to reduce by factor 10 the number of cyclones you need in order to perform a good statistics by simply incorporating spatial informations. In the picture, you can see the results that have been computed using this approach around the Guadeloupe Island. So black boxes for each position actually shows the reference value that you can compute of the significant water height using 2,000 simulations. The red lines here represents the values you can compute by using only 50 of those cyclones, and the blue ones shows the value what you can get using only 50 cyclones, but using this new approach. So you can see that is much better. And at the end, we decided to for simulating something like 700 cyclones, 700 simulation of water levels and waves to compute our statistics. So in order to perform those simulations, the first step to do is to build a mesh. So the model we currently use are unstructured models, use unstructured meshes. So we collected bathymetric data, and we realized this mesh you can see here with some zooms on Virgin Islands and French Islands in the Lesser Antilles. So this is a mesh that has a characteristic mesh size of 20 kilometers in deep ocean, and refines up to 300 meters on the coastline. And we have also an heterogeneous representation for the friction coefficient in order to represent the presence of a reef. For simulating waves, we use the very well-known in the worldwide community of researcher WaveWatch 3 model, which is a spectral model. As I said, is a completely unstructured model, and here on the right you can appreciate a validation we performed for this model on the Dean cyclone, using data from two buoys. These are data collection from Meteo France. While for the sea level, we used the in-house model WINA, which is an hydrostatic model, which is co-developed within a consortium of French institutes. It also has a non-hydrostatic module that is whose development is ongoing. It can work on spherical geometry, and of course it has atmospheric forcing. It is also unstructured, working with the discontinuous Galerkin finite element approach, and very important is HPC, and that's why it's very well suited in this case, because we have to perform a lot of simulations. So in these slides, you can see the validation of this model using the Irma hurricane event of 2017. So in the top, you have the images of the atmospheric forcing, so the pressure and wind fields that has been constructed. And on the bottom, this is the result of our model in terms of sea surface height. So you can appreciate the presence of the inverted barometer effect on the sea surface. and the effect of the wind which becomes very important in shallow areas. This is a zoom on the Virgin Island, and so you are able to appreciate the effect of the wind while the cyclone passes on this, which is a very shallow area, which is reflecting the distortion of this originally circular patch. So this again is the same simulation. This is just the maximum sea surface height all along the simulation. So you can distinguish very well the track of the cyclone. And those are probes. So it is the time signal of the sea surface on different locations along the track. So number one is Samantan Island, and those others are in the Virgin Islands. And you can appreciate that we have a global good match with observation, especially when we are very close to the track of the cyclone. But the results are becomes quite poor as far as we go further. We go far from the track of the cyclone. The main reason this happened is because our estimation of the pressure field is very poor with respect to what has been observed. Other source of discrepancies are the absence of wave setup computation in this model, and maybe also the coarse representation of insular shelf in our mesh. So this effect for the representation of the pressure field on the simulated sea surface site was something that was already stressed in previous work, in particular on this paper of Joyce 2019 by a Puerto Rico group of researchers. So once we have performed our 700 simulations using those models concerning water levels and waves, we are now able to perform our statistics. And here we compare what we get to what it was already computed in previous work, especially on this paper of Crien of 2015. So we are around the Guadeloupe Island, and for each point here you can see the 100-year return period value for the significant water height that has been computed in the study, which is the first column, and the value that exists in the literature, which is the second column. Of course, we have a discrepancy. So first of all, the value that has been computed in the literature uses 2,000 hurricanes. That's why we tried to compute the same value by using just the same number of hurricanes, but we fall again on a similar value here. So we started to try to understand why we have this discrepancy, why we display values which are much higher. And the answer we found is comes from this paper of Meyer 2022, where we actually see that each database, here they compared the 3 databases, has a different composition between hurricanes that belongs to different categories. So here we have all the categories from tropical storm to category 5. And we can see that our database store contains much more category 3 and category 5, category 4 also, with respect to the blue database, which is the one that is being used in this work. And of course, we have a very strong link between the category of the hurricane and the significant wave height that can be observed. And this explains the discrepancy that we have in the result. So we are now more confident in what we produced. And these are some maps, special maps that we can. Sorry. Yes. Sorry, I forgot to mention that the percentage of hurricanes in each category for our database is much more close to what exists in the reference in the IBETRAX database, which are historical data basically, than this MIT database. Okay, so here I've shown just some the result in some point close to the Guadalupe Island, but of course we can perform the same exercise in all the domain. These are results that we could perform, and the similar results are also available for the sea surface height, and will be available on the website, as Jan mentioned before. So now moving on our activity on tsunamis. Here, just to remind you, the topic was to assess tsunami exposure in terms of water levels and time delay. So there was a great work on the analysis of tsunami and earthquake catalogs, making a bibliography synthesis. And this work allowed us to identify 13 major areas, tsunamigenic areas, still in the hypothesis of worst credible case. Then, in order to build a scenario to be simulated, we have to, once a tsunamigenic area has been identified, we have also to design a geometry of rupture. So in this work, we starting from the 13 areas that I've shown before, we compiled more than 100 fault geometries, retaining 30 of them in the context of worst credible case. And the geometries that we retained then imposed us to refine the mesh that we use to perform our simulations in the generation regions, in order to better capture the phenomena that controls the generation. So we modified a little bit our mesh, computational mesh. And one can now just impose an homogenic rupture on the geometry and run the simulation. But in this case, instead of doing this, we use a new approach in the Caribbeans, which consists in performing several stochastic realization for the slip distribution for each geometry. Uses a toolbox that has been developed by a colleague, and it's called Rajan. And this implies that we have several simulations to perform for each geometry that has been retained. So this will make grow the number of scenarios to be simulated up to 300. For each rupture, then we can compute the displacement of the sea surface height simply by using the FFaultDisp software that implies the Okada approach. The simulation, once again, are performed using the WINA model. Here you can see an example of, so is the simulation of the tsunami 1839, inspired by the work of Boyer 2011. The interest of performing this case was to validate our model. And in order to do so, we compared what we get to what another model can simulate. So we used a very well-known model in the literature, in the community, which is FunWave TVD. And we can yes, and we can then appreciate from these signals that the two simulation results are in good accord, despite the numerical differences between the two models that are not really comparable. Okay, so once all the simulation have been realized, or the 300 simulation, then we could be able to produce this kind of maps of the maximum expected sea surface elevation, of the most important scenario for each sector, and also to evaluate the arrival times for each tsunamigenic area considered. Of course, this is not possible yet because computations are still ongoing, but this is an example of exactly the main kind of study that we performed on the coast of the metropolitan, on the Mediterranean coast of France metropolitan, and such kind of result would be available on the CARIB-COAST web platform. So now I will let Rodrigo finish the presentation.
Okay, thank you, Andrea. Just how to deal with coastal flooding, exposure, and risk. Two examples, one for hurricane, another one from Sumatra. Okay, this is not a product of CARIB-COAST. It's just to illustrate our work in this domain. Here, for hurricane 1928, we made a lot of historical research with the parametric shape, pressure decrease, with the photos, with wideness of water height, limits, etc. Okay, and we permit us to modify the track of to correct the track of this hurricane. After that, we use the same procedure that described by Andrea to generate the pressure field and the wind fields, and we compute with models, with hydrodynamic models and wave model, coupled to compute with the next width here, the flooding in Pointe-à-Pitre harbor. You have a Pointe-à-Pitre harbor here. Here you have a point, the time series of water level, significant wave height and wind speed and barometric pressure here. You can, here it is the moment. It's concerned the flooding of all this area, in particular in area of Mangrove. And we used two non-hydrostatic model. Here is a spatial model because here you have the two flowing types, overflowing and overtopping. Okay, with this coastal flooding, we combine with the distribution of the buildings in this sector, and we are able to compute for each kind of building, this commercial or industrial buildings with the houses and public building. We can have the number at the kind of exposure from the weak to the very strong. Is this the building when nowadays? Okay, it's not in 1928. It's if we have the same kind of cyclone, we can expect this exposition of building. Now from Sumatra example, here we go too far. We compute the generation with a CAD model, and we propagate DIMS, and we use nested grid to go to a 2.5 meters, including houses, building, and road, etc., to compute the coastal flooding. We validate here with field. After that, we work on building typology, different building from concrete to wood houses, We define damage scale from just crack to complete collapsed building. For each kind of building, we can establish a vulnerability function. Is the percentage of collapse of the building is depending of the water height, and we apply this in here. Is in Sri Lanka is the Gold Bay. Okay, is Sri Lanka. Okay, with this procedure, we can compute the building, the collapsed building. Here at the bottom at the right, you have the building close to the coastline are completely collapsed, etc. And of course, we validate this risk mapping with the census of this event, and we are in the 10 to 20% error. Okay, and in CARIB-COAST, we stop just at coastal flooding, not to exposure or risk. Thank you. That's all. I don't know if
we have two small questions in the chat. Maybe you can answer directly.
Mm-hmm.
Just ask the presentation. Maybe.
Where are the, excuse me, I don't have the question. Conversation. What's, do you have? Okay, for the number of the years that we have compute wave cyclonic or hurricane wave data, we use that storm database that can reproduce 1,000 years from tropical storm to category 5 cyclones. That our database concern 1,000 years. Okay, this is why we can compute a period of return of 100 years from wave 8.
How fast is the computation with Winer in comparison with fan wave? For this kind of simulations, we were like 2 times faster than real time on this mesh. The problem is that the comparison with respect to fan wave is not really but it's difficult to make a comparison because we are not using the same resolution at the coast. So it depends what we want to compare. So here in order to have comparable results, we use the structure mesh of 800 meters, which is something between 300 meters at the coast and 20 kilometers far. I don't know, Rodrigo, if you remember the coast to have a simulation on such a mesh with fan wave.
In fan wave is 600 meters.
No, 800. The resolution is 800 meters.
Okay,
but the cost for performing the simulation,
I don't remember.
Is maybe 6 times faster than real time. So with Winer is 3 times lower. But in the paper that was mentioned, we also since we are using a DG approach, we tried to understand also if we could use an higher order scheme in order to gain to use a more coarse mesh, but obtaining the same kind of results. And actually, for tsunamis, the answer was yes. We can have a mesh with only 600 meter resolution, so with like 50,000 elements less. To make our simulations, so we can increase a little bit the performances of Winer.
Okay. A question of one: what tool we use for suitable meshes? We use GIS. QGIS is an open source with a plugin is Gmesh developed by other people with our plugin and written in Python. And we can easily deal with the real data to measure in realistic cases. The last question is the boundary
data used, open access. Who provides the data? Historical wave height, wind speed, and bathymetry. So
historical wave height is from data source from voice you can retrieve. Okay, from NOAA, from Meteo France, etc.
For wind speed and pressure, you can you have a IBtract database where you can find the maximum wind speed and the track and the minimum pressure for cyclones. But you have then to use a parameterization in order to build up your pressure field and your wind field. That's why you may have some discrepancies with respect to the historical observations.
And we blend this cyclonic wind field with meteorological data coming from USA, from CFS video feature. Yes. And the bathymetry that we use here is coming from JEPCO 2020, and from SHOM, is the French hydrographic service, that we can obtain data from up to 100 meters close to the coast, the French area.
Yeah, the product is called Homonyme.
And it's free.
Thank you, Rodrigo, Andrea. We'll move to the next talk. And if you have any other question, keep writing it on the chat, and we will have a discussion session at the end so we can answer to other questions. Thank you.
Thank you.
You can share your screen, Julie, if you want. Okay. Fine. I'm not sure your mic is on.
Okay, is it better this way? Can you hear me?
Yes, thank you.
Thank you. Hello everyone, good morning or good evening, depending on where you are living. My name is Julie Dehaye. I'm a scientist at CNRS, and I work from Paris in a lab called l'Océan. And I'm a physical oceanographer. And I titled this presentation From Climate Change to Coastal Processes, What Can Be Done and What Remains a Challenge. And I wasn't sure of who was attending this webinar, so I started with very basic knowledge about what ocean modeling is. And I speak about the physical ocean here. And I wanted to start from the very basic, how do we study the ocean dynamics? So dynamics mean the temperature, salinity, and the currents, and any impacts they have on sea surface height. And so, of course, it all starts with bathymetry, because the bottom floor and the shape of the floor has a huge impact on the ocean currents, which then shapes the structure of temperature and salinity in the deep ocean and the surface ocean as well. So how we do this, we go with a boat and we take samples, or we drop a probe that goes down in the deep ocean, or we have the ArgoFloats that sample the ocean pretty regularly. This is a picture from a couple of days ago. Each single black dot is an instrument floating autonomously and taking vertical profiles from the surface down to 2,000 meters. But you can see in coastal areas, we don't have much. So it all relates on where the ship went to make measurements. And for the ocean currents, we also drop some current meters. We call them ADCP at the bottom. So the top left shows the anchor at the bottom that stays on the ocean floor. And the instruments will stay in the ocean for a couple of months, eventually a year if we're happy, if we're lucky. But this is the only measurements that we have for the ocean currents, really. So, of course, we also rely on satellite measurements that can see the color of the surface of the ocean that gives indication on the temperature or the chlorophyll concentration. That's to the central part of the figure. And of course, the satellite also gave the sea surface height anomalies, which then can give some information about the currents close to the surface. But this is not enough to really know the currents at depth. So it all relies on ocean modeling. Modeling is about solving some equations. Here, it's a shorter version of the primitive equations that we are solving when we draw models of the whole ocean. Of course, we have to discretize these equations because this is continuous equations. If we want to put them in a machine, it has to be in a discretized way. So we have to choose horizontal and vertical grids. And of course, we have to choose numerical schemes. This is a short example of different schemes for an advection of a peak. There are many recipes from the applied math world to solve those equations and bring them in a machine. And finally, we have to apply parameterizations for all the processes that we are not resolving. And also we have to decide on boundary conditions. So why do we do model of the ocean? In order to finish convincing you that this is a proper tool, even though it's uncertain. Well, it allows to experiment. I just put a suite of 2 pictures here of a model of the southern part of Africa, where we focus on Madagascar here. To the left is a sea surface height from that model, and to the right is the kinetic energy. And if I go quickly to an experiment, you see Madagascar is gone. So this paper, I really advise you to read it if you want to see how we can experiment with modeling. You see the impact of having or not having Madagascar to the east of Africa. Of course, we cannot do this with real observations. Modeling the ocean also gives us access to much more information about the ocean's current state. This is another study from colleagues of mine about decomposing the carbon cycle in the Southern Ocean as a contribution per water masses. This is something that we'll never have from observations. And finally, we do modeling of the ocean because it creates ocean variables where we won't never ever have observations. And that is the past and the future. So the past, any measurement that we did, we have it, but any measurement that we didn't take, we'll never have it. And the future, of course, will never be observed. And this is why we rely on models of the ocean and more precisely of the climate. So coupling the ocean and the atmosphere. So in the end, those beasts, which are called ocean general circulation models, so again, some wordings, they really base on the discretization of a set that we have to choose of equations and boundary conditions. Beyond this type of discretization, then we set configurations for a specific region or the global ocean, and they are related to the choice of resolution in time, horizontal and vertical dimensions. Then, depending on the resolution, we may decide to have some processes to be parameterized, because if the resolution is not enough to represent them explicitly. Once that configuration is decided, then we still have to make choices for a given simulation. So the issue is the initial state. Where do we start from? We have to decide on atmospheric conditions if the model is only an ocean model. We have to decide on the lateral conditions if it's only a specific region and not the global ocean. And eventually we can assimilate some observations. So why are there so many different model outputs? Well, precisely because of everything I said before. First, the different approximations that we can do on the equations to be solved. That's what defines a model per se. Then there are all these choices of discretizations, the schemes that also define what a model is. Then as we enter the world of configuration, well, every resolution is unique and associated with parameterizations for all the subgrid scale processes that are not explicitly resolved at that resolution. And finally, we also have to choose on the bathymetry and all the forcings at the boundaries, at the surface and at the lateral boundaries. So after this, you understand why the uncertainties in ocean modeling are so numerous. There are some uncertainties associated with the internal variability of the ocean. If you encounter any of those and you're performing your simulations yourself, then I advocate for performing the simulation with a different initial state. And you'll see that most often it really makes a big difference, even a couple of years later. Sometimes the uncertainty is associated with the external variability. Then we have to try performing simulations with different boundary conditions, both at the surface and at depth. Then sometimes there are structural uncertainties. They're actually always here. And they are associated with those choices from what defines a model, also with grid resolution. And finally, there's always some 3 parameters of the model. Sometimes they're associated with parameterizations, sometimes they're associated with other choices. It's important to play around with them. And finally, how do we do data assimilation? Well, I won't enter the details, but assimilation of data in ocean modeling is really about incorporating information from observations to make them similar, to make the model output more similar to the observations themselves. This is a picture from an example in the southern part of Africa, but it can actually be taken anywhere else. Why do we do this? Well, because we want to make predictions of future ocean circulation more accurate to begin on the state of the present day ocean. So for example, if there's a cyclone somewhere or an eddy somewhere, and we want to start from that state as close to the real ocean as possible. Also, if we want to understand previous patterns of variability, we want to make this ocean simulation the closest to reality as possible. So mostly it is mesoscale processes such as eddies that really benefit from this technique, because then we can really have the proper mesoscale process at a given time, at a proper space. And you'll see later that if we don't simulate data, then it doesn't work. If you are interested in those products, then I give here some examples of ocean products with data simulations. The European consortium CMEMS is also providing good quality of data simulated products. Now, if we turn to climate, well, in addition to all this, we have to ensure that the couplings are represented. So I was just speaking here about ocean dynamics, but in the climate perspective, you also have the atmosphere dynamics, the composition of the air, vegetation, of course, and anything that happens also in the ocean, like marine biogeochemistry, that includes phytoplankton, zooplankton, and all sorts of living animals. And of course, the sea ice and the continental cryosphere as well. And the couplings are very numerous. They're actually everywhere, which it makes a climate model that represents all this all together much more complex than just the ocean model itself. Now, regarding our contribution to the CARIB-COAST project, here at l'Océan, we were in charge of modeling the hydrodynamic conditions around the Lesser Antilles. And this is what we did using the NEMO model, which is from a European consortium. So you see to the top, the first configuration that we developed, which is at about 10-kilometer resolution. The color here is showing the bathymetry. And inside this large-scale configuration, we inserted a first level of zoom to refine the resolution to 3 kilometers, and we then inserted a second level of zoom to scale down the resolution here on the green area down to 1 kilometer. All these simulations are forced by atmospheric reanalysis, which means that we only have an ocean model that runs. At the boundary of this big model, we use those CMEMS conditions that I just spoke about, so they are simulate observations. So anything that happens in the real ocean there will enter the boundary. And we are simulating more or less the previous decade. And this is how we compare with observations of EKE. So EKE is the eddy kinetic energy at the surface. It's a good proxy for any turbulent activities happening at the surface of the ocean. So the observations are the top. They're taken by satellite, and you will appreciate how coarse resolution those products are. So we don't even see the islands forming the Lesser Antilles. And then to bottom is two versions of our model where we change the atmospheric conditions. So DFS5 is a given product, and AR5 is another one, which is higher resolution. And in the end, we decided to go for AR5 for reasons that cannot be seen here. But what I want you to have a look at is this time series to the bottom. When you look at the eddy kinetic energy, just average over the Lesser Antilles, and you see the differences between the two lines. So this is the eddy kinetic energy calculated in the model in the two versions, one forced by this product and another one by this one. And supposedly the two atmospheric products, they've seen the same atmosphere. They're the same type of product, assimilating atmospheric observations into an atmospheric model. And yet they give very different results. And then the answer of the ocean model is very different. So any peak that may represent the pathway of a cyclone or something is not going to be the same represented depending on the atmospheric condition that you put on your model. If we continue comparing, then we use tide gauges here because we do have barotropic tides in our model. And I only picked two places, Fort-de-France to the top and Pointe-à-Pitre to the bottom. So the good thing with tide gauges is that we have very long time series, so we can really compare details. You have here two versions of the model at two different resolutions, the blue and the magenta, but they really superimpose on each other. So resolution doesn't have an impact at all on the propagation of tides. And the observation is the black line. And there are times where it really matches. There are others where it's not so good. Unfortunately, there's many different timescales that superimpose. So usually we would rather do spectrum analysis to compare the models with the outputs. And so here again, the observations are in black and the models are in the colored line. And you see that we pretty much have similar spectra of variability, particularly peaks here that happen at the same amplitude with the same time scale. So we're really happy with the model output regarding the barotropic tide propagation. We're a bit disappointed that changing resolution doesn't have any impact, but it's better because it means you can run a coarser model that is cheaper. If we continue trying to find in situ data, well, then we hit a wall because there are not so many in situ data anywhere in the world, and particularly not around the Lesser Antilles. So we could put our hands into two sets of ADCP measurements. So ADCP is for the temperature, salinity, but mostly the ocean currents. That's what the most important that we want to validate in our model. And so one set was taken in 2017. That's to the bottom in the Bay of Fort-de-France. And then there was another one to the east of Guadeloupe in 2020 that I'm going to speak about. So for the first one in the Bay of Fort-de-France, you see here again spectral variability of the currents. I just saw here the zonal currents from west to east, and the observations are in black and the model is in pink. And you have 4 points here because there were like many instruments here. More or less, the agreement is good in this part of the spectrum from a few months to a few days. To the right-hand side, the highest frequency, the model is not matching observations because we're lacking high frequency atmospheric conditions. We only have 3 hourly atmospheric forcing fields, which doesn't allow us to have this part of the spectrum. But it's fine. I mean, we're happy with this 1 day to 1 month agreement. You see that the agreement is not good everywhere. It's not the same. But like this 0.3 here is very deep within the bay, and it's a very shallow area. So we expect that the bathymetry in the model was not good enough, was not high enough resolution to really represent what was making this processes here. If we switch now to the east of Guadeloupe, at this Pont de Flandre, this is the place where you see it's located to the offshore, and it's an area where the shelf is actually extended offshore. And so this is where we expected to see a lot of mixing because of waves, internal waves propagating and then crashing and inducing mixing in this place. So we're looking here at the bottom temperature, and we could have a little bit longer observations here. They last nearly a year. And you see the comparison between the observations in black and the model is pink is again quite good, showing that we're really capturing the processes of variability. So we're happy. But we are not so happy when we look at sea surface height anomalies to the east of Lesser Antilles. So here the picture is a bit sophisticated. I'll explain you. So to the x-axis is latitude, and so to the left is south, and to the right is north. And the vertical axis is time. So when you look at those blobs, this is anomalies that propagate south to north so south-north along the Antilles to the right of them. We know that, for example, there are North Brazil rings that come out of the reflection of the equatorial currents and then propagate along the islands. And so this is the observations, and this is the assimilated product that we use to put at the boundary of our model. So the two are very close. That's normal because that CMEMS is assimilating observations. Now, when we look at our model outputs, then it's totally different. And this is the model at 3 kilometers. So that's the highest resolution that we had covering this whole time period. And you see that in a statistical perspective, there's a good agreement. There's things matching. There's some bluish area where it's blue and reddish where it's red. But individually based, like one event by one event, it doesn't work. Although those anomalies presumably either come from the offshore or they're directly induced by local winds. And we do have the true local winds because we have assimilated atmospheric products. So it really shows that, yes, our model cannot represent this. And when we switch to the model at 10 kilometers, so the coastal resolution, again, we have two different versions, which are really, again, statistically, they are comparable, but detail by detail, they are not the same at all. So this is a bit disappointing. And also, we really can't say which one is the closest to the observations between the coarse model and the high resolution model. So this is my conclusion. I hope I wasn't too short. In the end, all our analysis of the spectra of variability show that we're very similar to the observations, which is good because it indicates that the local processes are very well represented. But at the same time, the individual events, like the sea level anomalies propagating from south to north, they're not well represented at all. And of course, we know that data assimilating and simulation would work, but also it indicates that there are structural biases in our simulations. There are some processes that we don't represent correctly, and so we don't have even the big anomalies, we don't have them at the right time and place. Also, we struggle to identify which are the benefits of increasing the spatial resolution from 10 to 3 kilometers. It's a huge increase in the cost of computation. So we won't run the 3 kilometer if it's not needed, and if it's coarser, then it's cheaper, so it's better. But at the same time, we know that at 3 kilometer, we can represent the bathymetry around the islands, which much more accuracy. For some application is very needed. For some others, it's not so needed. But we speak about coastal processes, we definitely need to have the 3 kilometer coastline or even the 1 kilometer one. But if we can't really assess the benefits of increasing spatial resolution in terms of representation of the processes, then that's a bit sorry. And finally, I think I'll take questions about this if you are interested, how to factor in climate change. Well, technically, it's not so difficult. We have to change the surface and the lateral boundary conditions. Of course, we have to find them and we have to make them or to extrapolate them from other available products. But overall, we can't evaluate or we can't assess the validity of our future simulations. So we only do this once we are happy with the present day simulations. And as you can see at the moment, we are more or less happy. There are some things which are quite good and some others which are not yet good enough to our records. So I'll stop here and take questions if you have any.
Okay, so you have a question from Juan in the chat. I don't know if you, since you was very quick, so maybe you Perfect. Can answer this question. And I don't know if there are others.
So I can see what kind of vertical coordinates has NEMO. So NEMO has many different coordinates at the moment. So you have the standard historical one was dead level, so vertical levels at the same depth. It has developed the sigma levels, and now it has the capacity to run with hybrid coordinates. For this particular configuration, we use the Z level, but we also are developing the same configuration with CROCO, with sigma level, and we will be running NEMO in sigma level as well. We don't expect that it has a much impact on this type of configuration based on expertise that we have in other regions, because it's high enough resolution and it's high enough resolution with the resolution that we have for bathymetry. So we're using the JEPCO product for bathymetry, and we don't have so many products for bathymetry in terms of high resolution or higher or more confidence in the data. So regarding this, it's not so easy to switch to even high resolution because we don't have the information on the ocean floor.
Yeah, so in my presentation, I will go a lot into this issue with the coordinates and the shelf in Puerto Rico. And so I use ROMs, which is sigma following. And I'm pretty much at the point of just thinking that it will not work, just because at least in Puerto Rico, the shelf is only like the widest is like 13 kilometers, and I'm using like 1.5 kilometer, and the drop at the shelf is just too steep. So you will see later in my presentation, it took me a lot of handwork and smoothing and working with the bathymetry to even get something similar to a curve. So I think in theory, I think if there was a model that could do, I don't know, suddenly convert to like hybrid coordinates right on the shelf, that might work. But it's I can see why you said that going to 3 kilometers might not help too much, because if you have, at least what I'm seeing is like with more resolution, the shelf becomes even more dominant, and then even at 1 kilometer is not enough. So I imagine I will go, to fit properly a curve to the drop. I think I will have to go down to like 50 meters, which that would be like completely insane on 3D. So it's really nice to see your results, because I'm kind of getting at the same point that I don't really know, what would be the right way to proceed. just because the bathymetry it's so difficult to deal with.
Yeah, so thank you. I'm glad that you are that my contribution helps to interpreting your results. I think that I agree with you that in theory we would have to go to much higher resolution, like 50 meter, to really have the proper drops in the shelves. Unfortunately, we do not have observations of the bathymetry at that resolution on a large scale. And the other issue is we're lacking observations of the currents anywhere at any resolution enough to validate those models. So pretty much you change something in the bathymetry, it's going to change your currents, but you don't have anything to say if it's better or not. And that really is the issue that we encountered. So in the Bay of Fort-de-France, there are some processes happening in the deep ocean, but we only have like 5 months of measurements of the bottom currents, which then shows that our model still is wrong, but we really can't say why, and we can tweak the bathymetry and make it crazy or just to fit the observations, but the validity is very limited and it's just overfitting to the data. So for me, there really is a lack of observations of the high resolution bathymetry, but also on all the hydrodynamic variables that will allow us to disentangle from different model experiment, which is good and what is not good. Now I can see there's another question. Why did you choose NEMO instead of any other model like WaveWatch 3 or SWAM? Okay, so NEMO is not a wave model. NEMO is an ocean dynamics model. So NEMO solved equations for temperature, salinity, and ocean currents through the whole water column. And WaveWatch 3 is not representing this at all. And SWAM, I think it's a wave model as well, unless I'm not super accurate. And that makes a big difference. So with an ocean dynamics model solving all the hydrodynamics, then you can look at the currents at the bottom, at the surface, in the mid depth. You can look at changes in the heat content of your water column close to the coast and to the offshore. So you really don't tackle the same type of scientific questions with its different models. With a wave model, you only have an idea of what happens at the surface of the ocean in terms of dynamics. You don't see any changes in salinity or temperature or how much those will affect the currents ultimately. And then there's a question about internal waves in the model results, and do you think they play an important role in mixing in this area? So yes, we see internal waves in the model results, and yes, we think that they do interact with the bathymetry. This is what we were after in Banc de Flandre in the comparison. But again, so I do think they play an important role in mixing, but I don't have a proof for this because I couldn't really show like with and without the internal waves. So I'm still doing some analysis to prove it. But yeah, it's not super convincing yet. Did you consider nesting? Yes, I do consider nesting. If everything that I showed you is actually having a regional configuration covering the whole Caribbean area, with 2 levels of nest embedded, and those are two-way nesting because we want to fix the large-scale simulation with the nesting, with representing the local processes at higher resolution. So those two nests have a factor 3 of refinement, so which allows us to go from 112 degree to 136 and ultimately to 108 degree of resolution.
Okay, thank you, Julie. It was very clear, very interesting. We have just a last question.
Do you nest around the islands? So yes, I do nest around the islands. But if my previous answer didn't convince you, it's because we are calling nesting different. So maybe what I haven't said is that the grid of NEMO, like all other OGCM, is a rectangular grid, which is regular. And it is not a grid that allows to have refinement in some places like finite element models. So here we do have to refine everywhere in a subset of the grid. And we can't just have more grid points around the islands and less offshore. To my experiments with OGCMs in many places around the world, the issue with the unstructured meshes, when they're not dynamic, is that the boundary where you have the refinement and where you don't have it has a huge impact on the solution. So I'm not talking here about the dynamic meshes as you've just seen in the presentation before, where you refine and the refinement moves around with your simulation. I'm talking about static refinements. those have a big impact on the solution. So ideally, we would like to have a large-scale configuration with refinement just at the place where we need it, but we don't have that tool yet. You mean having an extra structured nesting for the island region? Yes, so we are developing at the moment an extra level of nesting just around Guadeloupe and Martinique, pushing the resolution to 100 meters, which will be done with Croco, because Croco is more suitable for resolving the process at that scale. Unfortunately, again, we hit the issue of the precision of bathymetry. So we can do 100 meters, but we can't do flat bottom. We have to have some include on the bathymetry. And this is something that we're missing. We're also missing, of course, atmospheric processes and atmospheric products at that scale that are relevant. Because if we want to look at coastal processes at the time scale of, let's say, a day, then we need to have super high frequency atmospheric conditions, which we don't have on the large scale. So we should have to couple to an atmospheric model like WASH, but then that's a whole other story.
Okay, Julie, I interrupt you. I can see that there is one more question, but maybe you can answer in the chat. So we can move on with the next presentation, which is made by Erika Badi and Marc Pavec from Ifremer and Actimar. So I will ask them to take the hand and share your presentation. Thank you.
Yes, thank you. Yes, I will share my screen. Okay, do you have my presentation on screen?
Yes, we have it.
Okay, so I'm Marc Pavec from Actimar. I will present a work that we have done for in the frame of the CARIB-COAST project with Ifremer, and Erika Badi from Ifremer is also in the conversation and can answer the question during or after the presentation also. So we'll talk about what we did in terms of numerical modeling of the currents around Guadeloupe and Martinique. So thank you very much, Julie, for your presentation before my presentation, because it was an excellent introduction to what I will present now, because we made something really similar to what you presented before, but maybe with different objectives and different techniques. So I will detail the 3 steps of the work we have done. First of all, before building our modeling system, we had to collect data and information about the area to get more knowledge about the area and to get in situ data to validate our models. The second step was the model construction and, of course, the validation against the data acquired in the first step. And after that, the objective of our model was to build a 5-year hindcast of currents around the islands of Martinique and Guadeloupe. So I will present all of these 3 steps in the following. So first of all, data acquisition and analysis. In the frame of the CARIB-COAST project, 2 kinds of data have been acquired. First of all, we had 12 ADCPs to measure currents, water level, and some other parameters that I will present in the next slide. And we also had 12 drifting buoys at the surface. So the aim of these 2 campaigns was to measure the current speed in our area of interest. So first of all, the ADCPs. 12 ADCPs were launched around the islands, 6 for Martinique and 6 for Guadeloupe. You have here the green dots represent the locations of these ADCPs. The main constraint for this campaign, that was the ADCPs had to be in water depths of about 50 meters. Where you know that the bathymetry falls very quickly as we go offshore. So that means that 50-meter depth is we could only have ADCPs in areas very close to the coastline. So here you have the locations of the ADCPs to cover the coastline of the two islands. And the second solution used to get information about current was to deploy drifting buoys in the area. It was done in two operations, 6 buoys the first time and 6 new buoys the second time. I will not talk a lot about this data set because it was not used for the validation of the model, and ADCP data was used, but all the data exists and is available for use for other projects or follow-up of this project. Just a word about ADCP measurements. ADCPs are on the bottom of the ocean and look towards the surface. They measure current speed and direction all over the water column. They can also measure the water level. And in this case, we also had the information about water temperature at the bottom and about wave characteristics. Here again, we didn't use the wave measurements for our needs, but this data also exists and has been analyzed in the frame of the project. The ADCPs were operated by Nortec it was 2 years ago in 2020, and the campaign took place from August to December 2020. So here is an illustration of what we get from these measurements. I will not present the results for all of the 12 stations, but just 2 significant stations. So what we can see here, it's the current speed over the water column between August and December 2020. So the time axis is here. So you see the measurement from August to December, and here you have the water depth. So the cells at the bottom of the plot is the value of the current at the bottom of the ocean. So what we see here, we see that we have a high variability in current speed of about 0 to 1 meter per second. Well, I didn't say that the station represented here is Banc de Flandre. If we go back here, Banc de Flandre is the same station that Julie presented before. This one, the easternmost station in Guadeloupe, quite offshore from the island. So what we see, current speed, maximum current speed of about 1 meter per second, a high variability in current speed with several examples of highest current speed with no regularity in the occurrence of such events. That's interesting. This station is quite offshore, so it's not dominated by the tidal signal. So we can get information probably from the general circulation around the islands, not only a very local, very coastal processes like we have in most of the other stations. Second example I would like to show, same principle of the plot. This time we are in Fort-de-France, so the Bay of Fort-de-France, Caribbean coast of Martinique. We see that we have a completely different current signal here. And the most striking here is that the maximum of current is always detected at the bottom. That's very unusual and that's a very particular situation. We also see this very regular alternation between low and high currents. And this is clearly the signature of internal waves. It was known that this location was a hotspot for internal waves, and it was confirmed by the measurement. This very strong signal at the bottom to our opinion, was clearly a signature of internal waves. So after this short presentation about the measurement acquired at the beginning of the project, I will present the modeling system that we have launched and how we have validated this modeling system against the measurements. The model characteristics. So first of all, the model we used is model Mars 3D. Mars is a model developed by Ifremer for several years and largely used for coastal processes all over the world. Yes, the discussion was about nesting just before my presentation. So here we see the nest that I used to build my model grids. I have a first grid here, which with a resolution of 4 kilometers and 2 zooms into that first grid. The last one here, which contains Guadeloupe and Martinique, has a resolution of 500 meters. All of the 3 grids works with 30 vertical levels. My atmospheric forcing was CFS-V2, which is a different product than the one used by l'Océan in the previous presentation. And the oceanic forcing came from an ICOM model at a resolution of 1/12 degree. And we had to add a tidal forcing at the boundary. The tidal forcing came from the product FES 214. So that's for a general description of the model. What we had to validate the model. So as I said, the ADCPs that I presented before, and also external sources. We used surface current from measurement, from satellite measurements. We used the product Globe Current and OSCAR. And also we used satellite measurements of temperature and salinity to validate our models. The first example I show here on validation is about water level. First of all, because it works very well. So here I present the results for a station named Caravelle. Caravelle is on the Atlantic coast of Martinique. You can see the small dot here on the little map. So what we have on this plot, maybe the most readable is the one in the right at the bottom, the superposition of the curves of the model. So the model is in blue, the prediction of water level in the model is in blue, and the measured water level is in green. So we see a good adequation between the two curves, a sign that the model is able to represent correctly the tidal signal, at least water level at this station. The scatter plot here confirms that there is a good agreement between the measurements and the model. And I present the results here for the point Caravelle, but it was the same for nearly all of the 12 points we had around the islands. And we show in this table the error between the model and the measurements. The error is estimated as the root mean square error, RMSE, in meters. And we have here the errors for each of the 12 stations mentioned before. So we see that the mean error is of a few centimeters, 4 to 5 centimeters, for all of the stations, confirming that when we talk about water level, the model was really good. Here I present the Fourier analysis, to the spectral analysis to show that the model is able to represent the tidal periods that are present in the signal. So we are again in Banc de Flandre here in Guadeloupe. We see the two peaks corresponding to the main to the main periods present in the tidal signal, semi-diurnal signal and diurnal signal. We see that both in the model and observation, we find exactly the same peaks for these two periods. So we concluded that the model was able to represent the water level and especially the tidal signal around Martinique and Guadeloupe. So after that, we have to talk of the validation on current speed. And the results were very good for water level and not as good for current speed. So we have to find explanations for that. So here I present the results again for Banc de Flandre, the station that I presented first. So you remember the current peaks with a high variability, maximum current of about 1 meter per second. Here is the results in the measurements, the same plot that I showed before. And here is the same plot, the same period, same location into the model. So if the model was very good, we should have nearly the same on the left and on the right plot. Obviously, it's not the case. But we estimate that the model is not too bad if we look in details, because the model also shows a great variability. The order of magnitudes of the current are not too bad. We also have the same color bar here with the same almost the same colors in the plot. So we have maximum values of about 1 meter per second. The order of magnitude of the current is not too bad. This event of high current is well represented at the beginning of October. So the model is able to represent the dynamics in the area, but is not able to predict exactly when these events arrive. Another example here, completely different. Again, it's the Bay of Fort-de-France with a very special plot with the highest currents at the bottom of the ocean. Here again, the measurements. And on the right, the same in the model. So here we can say that the model completely missed this strong signal at the bottom of the Bay of Fort-de-France. As I said before, we think that this is mainly due to internal waves. Our model, Mars, is a hydrostatic model, which is not able to represent fully the phenomenon of internal waves. So we didn't expect to have a complete representation of internal waves, but we were expected at least a signature of internal waves into the model. And I have also to say that the resolution of 500 meters might be too coarse to correctly catch these internal waves into the Bay of Fort-de-France. But what we see in the model, we also have a small accentuation of the current speeds at the bottom. We don't have the order of magnitude, but we can see that currents are not completely zero at the bottom. So maybe the model is able to represent this phenomenon, but further parameterization would need to be tested, and maybe a refining of the grid would be necessary to enhance this signal and get something closer of what we have in the observations. So the main results about the validation. Tidal level is okay in the model, but we have a high variability in current representation. And what we have identified is that the main source of error in our model was the boundary conditions that we used. As I said, we used a configuration of HICOM. And I show on the following slide that on the particular case of October 2020, so just in the middle of the measurement campaign, HICOM completely missed some events that were recorded in measurements. Here on the left, we have, so I always represent the mean surface current during the month of October 2020. Here on the left, we have information coming from globe current based on satellite measurements. We see a very strong current here in the south of the area, which is completely missed by HYCOM. So our model, which is represented here, at least the grids are represented here, is just a zoom into HYCOM. So it's completely impossible for our model to represent correctly what happened around the island in my small box if the boundary conditions missed completely very powerful events such as the one we have here. So our conclusion was that the main problem in our configuration was the boundary conditions that we use. And of course, an idea to improve our modeling system will be to test new boundary conditions to improve our results. So after this validation, and despite all of the problems we had and all of the problems we identified during the validation, what we have done with this model. The main objective of the project was to build a 5-year hindcast, and that was done at the beginning of this year. The hindcast is now available. It covers the period from 2016 to 2020. And 3D currents, speed and directions are available, as well as temperature and salinity and water level. The temporal resolution is 3 hours, and the spatial resolution is 500 meters. Files are available in an SCDF format and are available as an output of the project, as a deliverable of the project. What can be done with these results? So as I said, the model is not precise to represent day-by-day events. You can't say that an event observed will be represented correctly into the hindcast. But the model is correct to represent the dynamics of the area. So if we look not at single-day results, but if we look at a larger time scale, for example, monthly means or seasonal means, the model is correct. So we can use it to gain information about circulation around Guadeloupe and Martinique at those time scales. I represent here the mean current around Guadeloupe in August 2018. Here the same around Martinique. Mean current speed at the surface during the month of August. We see the circulations, typical circulations around the islands, between the islands, with very calm waters in some part of the islands. So these kind of maps could be very interesting to document and to get information about the surface circulation. Here at the bottom, it's the same, but not for surface, for deep currents. Here it's 1,000 meters in Guadeloupe and 800 meters around Martinique. We see here again, very, very interesting results with this counter current in Guadeloupe here, which is very well represented in our hindcast. The current, that means that the deep currents are completely different than the surface current around Guadeloupe. While in Martinique, deep currents are not too different. We also have a circulation between the islands, quite similar to what we observed at the surface. So that's the kind of information that we can get from the existing hindcast. The perspectives now that this work is done. So as I said, we think that we could improve the model with better boundary conditions. And what Julie presented before showed that better boundary conditions probably exist. We could also refine the model by additional grids. So we could imagine a grid at, say, 100 meters around Martinique or around Guadeloupe over smaller areas. And the results can be used for analysis of the regional circulation around the islands. For example, for the computation of Sargassum drift, maybe for study of sea level variations, or for a study of the deep water circulations. So that's all for my presentation. Thank you for your attention.
Thank you, Mark. I'm a little bit lost. There has been a lot of exchanges in the chat. I don't know if there are still some questions that didn't receive an answer. If it's the case, please write them again. Otherwise, we can simply go on at this one. Okay, yeah, there's a question on the model of turbulence. Maybe you can answer to this one.
The model of turbulence in Mars. I have to check which one we use because honestly the model was built I think 3 years ago. I don't remember exactly what is done, but I will check and answer in the chat.
No. Okay.
In Mars, we have the choice between several models of turbulence.
Yeah, so that's an observation by Juan on the circulations.
Yes, you're right. The pattern of currents in our area is not purely local. We need to take correct information very south from our area.
Okay, so the next speech will be held by Deborah. Hello. So.
Hi. Hi, good day, everyone. I'm just going to start sharing the presentation just now. Okay, can everybody see and hear me? Hear me and see the presentation, I should say.
Yeah, we can see. It's okay. It's okay.
Okay, so I'm just going to do a short presentation on some short-term observations of coastal processes on the east coast of Trinidad. My name is Deborah Villarreal-Lam. I'm from the University of the West Indies, St. Augustine campus, Trinidad and Tobago. So what we're going to be...
Sorry, Deborah. Excuse me, Deborah, but we cannot hear you very well. Maybe your mic is moving on the...
Should I start again? Is it better or worse?
Maybe you have just to approach a little bit your microphone to your mouth.
Okay, is this better or worse?
Yeah, I think so. Thanks.
All right, no problem. All right, so I just started off just briefly saying my name and what I'm going to present today. Give a little bit of context. Trinidad and Tobago is located off the coast of South America. So we see here South America. So this is Venezuela, and this little tip you're seeing here is part of Venezuela, and this is Trinidad, and this is Tobago. We are a twin island republic, and the measurements will take place along the east, exposed to the Atlantic Ocean. So we have some data collection going on the East Coast. So 2 data points really are aligned to the CARIB-COAST project. So we have some video data being collected here in Manzanilla on the northern section. And you see the coordinates for that across on this side. And as part of the CARIB-COAST project, we have some wave data being collected across here in Mayaro. And then I also have some additional video data coming in at Mayaro section. So it's being located at this point here on the eastern coast of Trinidad. What are we doing? What is involved in the video data collection? I'm going to speak specifically about the camera system at Manzanilla. It's located at our beach resort. We've been given permission from the owner of the resort to house the camera there. So it's at Manzanilla, the Simply Beautiful Beach Villas. We have three 5-megapixel cameras. They're contained in camera enclosures. The data is being stored on a recorder with a 4 terabyte hard drive. It's have a PoE switch that's powering the cameras and UPS backup. And all that is contained in a weatherproof enclosure. The system is powered by solar. So we have some solar panels on, well, I'll explain where they are on the roof of the structure, as well as some batteries. And this data collection started in 2022, the start of June 2022. We were supposed to start since 2020, but the pandemic delayed us significantly. When we visited the site in 2019, this was the site, and we had identified a location for our camera system. So the site was basically free of any obstructions. This is the university van here, and we were going to place the camera just a little bit seaward of where you see this van here in this picture. But that was in 2019, and then we had a 2-year delay. And when we went back in 2022, after we had been given permission to go ahead and use the beach, you see here, this is in June 2022, and this is in May. In June, you see the area has now been built up. There are a lot of structures there on the site. It's been quite developed. And this is the view we get in May. One thing I just want to point out here is this was it in May, and we had no sargassum on the beach. And then when we went back out in June, you see the beach littered here with the sargassum. At that time in June, we put down some little markers on the location to begin our data processing of the video data, but that is still ongoing. Okay, so the cameras were decided to be placed here. It was intended to be a standalone system, which is this. This is the system we have at Mayaro, and the intention was to be a similar system. But of course, as I just mentioned, because of the development at the site, we had to make some adjustments to what we were going to do. So this camera was supposed to be a standalone, powered by solar, and this weatherproof cabinet was supposed to sit somewhere around here on the whole system and be a system where we can just not be a bother or interference anyone on the side. But we had to do a little bit of adjustment, and this tiki hut, I think that's what it is was just where we wanted to place the cameras. So we actually got permission to place the 3 cameras, which you're seeing here at the top of the structure and below the roof level on the hut itself. Now we had to do a little bit additional work because we had to now wire, and this is what you see, the trunking that actually goes underground because the site is used by a number of tourists. It goes underground and is buried, and it goes to the little security hut at the back. So the cameras are enclosed at the moment in these enclosures, and this weatherproof enclosure that was initially intended to sit on the base of the pole is now actually inside the security hut, where we are housing all our information. We don't have I don't have the raw data yet, but I just got a little snapshot of the 3 cameras. They're operational. You get a little bit of a view of what is happening. You see the water line. We're able to see where the water line is at the northern, southern, and just in front of our beach. So it's just to now start processing that data set. Considering the current data that we're collecting as part of the CARIB-COAST project, it is located in Mayaro, and the reason why I placed the ADCP there is because it's a little bit more protected and less prone to damage or moving while it's deployed. So that's the reason why I had decided to place it at Mayaro. It's the RDI Teledyne workhorse. We place it in about 7-meter water depth. It's collecting hourly wave and current data. The current data is collected over 10 bins. The first bin is at about 1.06 meters above the bed, and the bin size is 0.5 meters. This data collection started on the 13th of April 2022, and we plan to end in November 2022. So it's still ongoing. So I have some data sets up until about July, and what we've begun doing is processing those wave and current data sets. So the purpose of the data processing is just to clean up the data, condense to any useful statistics from the data collected. So we derive some basic statistical parameters, max, min. We do some persistence statistics. We look at some joint probability of the data, as well as try to investigate any trends or correlations in the data. So I'm not going to present a whole lot of what we've done so far with the data, but just briefly some of the output in a couple of slides coming. So we did go through the cleaning up of the data, this initial pre-processing step. We identified any gaps in the data. We didn't have many for the data we've collected, just 1 or 2 data points that were not filled. And we would remove any erroneous data if we see that the data appears to be coming from a failed measurement, and that is completely removed from the record. Okay. So specifically on the wave data, we can do some grouping of the data, which is one of the things that I had done with the data set. So we group our wave heights, wave periods, wave directions, and it will continue until we have completed our data collection. So the category widths for like the wave heights will be 0.5 meters, the wave periods is 1 second, and then the wave directions are 30 degrees bins. We have grouped our data in. I try to identify after binning the data, what are some of the probabilities of each of the wave conditions in terms of wave height, period, and direction, and looked at also some joint probabilities for the wave heights and periods, as well as the wave heights and wave directions, and again, produce some persistence statistics for the data set that we have so far. So coming out of that analysis, the wave heights are grouped into these bins. We only had data over the last few months coming in the first 3 bins, with most of the data existing in this bin right here between 0.5 meter and 1 meter wave height. So we have a probability so far of 0.834 of that occurring. For the directions, we see the directions are given here, some group tag name. This is the standard one we use at the department. And then we have the category for each one of those. So we have data, the first 2 categories. So we didn't have any waves coming from between 0 to 60 degrees. That's on a bearing of 0 to 60 degrees. And then with the most dominant direction existing in this 90 to 120 degree bin. And so the probability of that is about 0.86. Then nothing after 210, which is expected because we are on the east coast of Trinidad. Concerning some joint probability of occurrence, so we see again, which is as expected, the probability of the waves in this wave height 2, which is at 0.5 to 1, and well as this D4, which is that this bin right here, the 90 to 120. We see that is where we have our greatest probability of occurrence, but we see some other data sets scattered as we look at this joint probability chart here or table. We also looked at the persistence statistics. So what this table is showing is the probability that event A is going to occur given that event B has occurred in the previous time step. So we see generally that that probability of occurrence, that persistence, is you have a larger probability that a wave of a similar height or magnitude will occur in the next time step. But there is some deviation across there, but it's small so far in the data set. Okay. We did plot some time series. So this is the time series for the wave heights, and of course generated some probability density functions. We do fitting to the histograms or the PDF, so we get an idea of what will be the best fit PDF for our data, and it will be completed once we have our full data set. We do this for our wave heights, our periods, and our wave directions. And just to highlight here, you see that wave direction is peaking just where we expected based on our probability assessment. So we have that sort of corroboration across all the different types of output that we generate for our wave data. Okay, and again, because we are on the East Coast, we don't see that range beyond the 180 in terms of the direction of the data. And it's speaking to just what we expected because we're being driven by the northeast trade winds. Right. For our current data, we do plot some time series for the currents as well. What I have extracted from the current data is we look at there are 10 bins. So I look at the one closest to the bottom. So I have a, I don't know if you can see it too well. I have a bottom current. I pull out the information from the topmost bin. So I have my surface. Then I have a near surface. I do a depth averaging, and then I look at the mid column. So that is what is overlaying here. It's not too clearly discernible, but the idea is when we're doing our correlation analyses, I want to identify which is the optimal current that will match when we're looking at tracking, let's say, relationships with our movement run-up, if we have any relationship with the run-up, our wave conditions, etc. So we have these 5 types of currents that I'll be using. Just for the depth average one, I just put here a plot of what that histogram would look like. And again, we want to fit these to distributions if we want to generate output for just general description of the site. For the current magnitudes, we do this color contour plot. So we have the time on the x-axis, and we have the depth. So it's just about 6-7 meters here. And I just plot the magnitudes, which are given in millimeters per second. So we see the variation in our currents across the depths and, of course, over time. One thing also I did as well is we looked at those magnitudes, we bin them and try to identify any outliers in the data set. So this box and whisker plot down here to the bottom, we see that just based on the plot itself, that there's a lot more scatter in our data at the surface, because bin 1 is closer to the bottom, bin 10 is closer to the surface, and there's a little more scatter in the magnitude data at the surface for our currents. So the current directions, again, I did something similar. So we have the bottom, surface, near surface, depth average, and mid column. I'd hope that this would have been a little bit clearer to see that the values don't always overlap. And that is the reason why I disaggregated the various components for the magnitudes of the currents as well as the directions. So you see here in this particular graph that it does not overlap exactly based on where we are in the water column. Again, for the current direction, we plotted this color contour plot with time and with depth, and you seeing the changes taking place in the directions of the current over time and across the water column. This box and whisker plot was also plotted for the current direction, and it's different to our current magnitude. What we saw is that near the surface, which is at my bin 10, you have less scatter. In fact, we had no data we could categorize here as outliers, whereas closer to the bottom of the water column, we see a little bit more scatter in our current direction. Okay, so that's just something that we're picking up as we're going through the data. So just to end, that's just what we've done so far. We, of course, have a couple of things still left to do. We have our video data to continue processing, which we intend to use get some wave run-up data extraction. We want to investigate any correlations between, of course, waves, currents, and wave run-up in the first instance, which is one of the steps that we plan to take. We want to compare, of course, our run-up output to any standard wave run-up formulae and see if we can derive what is the best one to use at this site on the East Coast for predicting wave run-up on the East Coast and looking at extreme and non-extreme conditions. One of the things we want to do is really highlight that extreme and non-extreme differences, see if there are any differences in those conditions, because luckily, I don't know if I should say luckily, but we managed to pick up a storm during this particular data collection campaign on June the 28th. We had a tropical storm that made landfall or hit us in Trinidad, and we were able to capture, of course, the video data as well as the wave data, because both instruments were deployed at that time. One additional thing we want to look at is we were able to capture that sargassum cycle at the site, and so we want to be able to document those changes at the site, which was not part of the initial intention for the data collection, but as we have the data, we want to go ahead and do that. So that brings me to the end, and that's it. Thanks.
Nice. Thank you very much, Deborah. I didn't see questions for the moment. Maybe once now. Yeah, maybe you can answer to this one, and then we go on with the next speech.
If you did the right.
Okay, so I think, yeah, Deborah, will you derive wave data from the video data? I'm not sure if I hadn't intended. I know it's something that we can do, but I hadn't intended to do that, but it's something possible. I'm not sure how much we will see effectively once we start to look at the video data in detail. So I do see some distance offshore, not as far as I would have liked to see because the pole would have been taller, but I will see if we can derive some of the data from the video camera, but I will have to compare it to our model data because I do have a model for the east coast of Trinidad and Tobago, and it's been validated, so we can compare it to whatever is coming out of that model data and see if we can get some useful information from the video data as well. So again, it's something that I can do, and we can try to do that as well. Yes, that is why we haven't begun to do our data processing as yet. My student, Shani, is using the data as part of her research. So she is actually supposed to go on site to start because her background is in geomatics and geoinformatics, and so that's what she's actually going to be doing with the data. So she's the one who had assisted me with processing the data at Mayaro, and she will do so for this site as well. So she and the geomatics department they have that in hand. All right, no problem. But as I said, I'm not too involved. I get the output, and so I see what is done at the end, and I'm not too involved in the hands-on part of the actual processing itself.
Thank you. Thank you again. So maybe if there are other questions, please, you can discuss in the chat. I don't know if Chris is here, already connected, or if we go on with
yes, I'm here.
Yeah. Okay. So please share your screen. Please.
Okay, hi. Can you see my presentation?
Okay, now it's okay. Thank you.
Okay, excellent. Thank you. Good morning, everyone. It's a pleasure to join you here at this workshop. Today, I'll be discussing, at least presenting a little bit of preliminary results, really, from some work that has been going on for a very long time. In Jamaica, we have been looking at a location at White House. So I was at Leiden University College last year, and I had one of my bachelor students working on this work. So it's myself, Chris Daly, Milva Bon, my student at Leiden University College, and I also extend some credit to Jaap Nienhuis, who's also in Utrecht. We worked on this field data collection together in Jamaica. So,
Chris, could you please put your slides on full screen?
My slides are on full screen. Oh,
we can see all the window, but not the full screen.
Okay, maybe I should change up. So when I press F5, sorry, I come here. You don't see that full screen, Jan?
No.
No? Okay.
Are you using a multiple screen?
No, I only have one screen. But apparently when I click F5 to do the presentation. So let me stop presenting and I share my entire screen. Share screen number 1. Okay, and if I press F5, do you see the entire screen now?
Yes, that's fine. Thank you.
Okay. All right, good. Yes, so as I mentioned, my co-authors Milva Bond and Jaap Nienhuis. So I will start by just giving a little bit of background. I know everyone here is familiar with the important role that coral reefs play in providing coastal protection, especially on the rising sea levels. And there's been some lovely work done already on this topic, looking at how reef structural complexity can help to reduce wave heights, especially during extreme events. And changes in reef ecology will, of course, affect hydrodynamic and morphodynamic processes in areas, especially fringing reef areas. So in Jamaica, we have quite a number of fringing reefs. So these are shown in blue here. The area that we have looked at is White House, so in the southwest corner of the island. But I think this area is quite representative of a number of other areas where we have fringing reefs and shallow lagoons behind. And here, if we zoom in a little bit, we can see that we have this nice embayed area and a lot of small fringing reef blocks here. So some of them are continuous over quite a long distance. Others are some small blocks with small gaps in between. Now, these reefs, of course, shelter the lagoon quite well. So we have depth-induced breaking over the reef, but also we can consider other, let's say, ecosystem, let's say, constituents in this case, such as seagrass. So in all of these lagoons, we have very dense seagrass beds, and that also adds to the dissipation of wave energy. In this bay as well, we have the very nice Sandals White House Hotel. So that's, I think, the main development in this area. For the rest, the bay is quite natural in terms of its in terms of development. So in terms of human impact, I think it's quite minimal. I mean, even though we have this large hotel here. So this makes it a good start for doing some of these studies. If we look at the wave climate for this area, we generally see that we have waves between, let's say, very calm, almost 0.1 meters up to a little bit more than a meter in extreme circumstances. When we have hurricanes, which are, of course, quite infrequent, then we can get waves up to 4 meters. But in the general day-to-day climate, it's usually around 0.5 meter wave heights coming from the northwest. So that's the general description of this area. We have tried to simulate this bay using XBeach. So XBeach is a morphodynamic model, hydrodynamic and morphodynamic model. In this case, we've been using it for hydrodynamic studies primarily to start with. And in this model, we can simulate reefs by adapting bed friction. That's one methodology that we could use. We could also simulate it as a type of vegetation. So there is a vegetation module in XBeach where you can input certain parameters for the vegetation, such as the stem length, the density of the vegetation, the drag coefficients, and these things. That takes the vegetation into account in the flow and hydrodynamic calculations. And in general, there are two ways of doing XBeach simulation. So one is this surf beat approach, where the wave energy is propagated in the model over, let's say, larger grid cell sizes. Or if you really want, you can resolve individual waves with the non-hydrostatic version of the model, And this includes both surf beat and individual waves. Now, the non-hydrostatic version of the model, of course, requires a much higher grid resolution. So we've avoided using that type of simulation setup. We've used the surf beat approach, which will allow us to have a grid area of around 5 kilometers and a runtime in order of 5 days. So that's just about how long we can manage with individual simulations. So the data that we have includes some wave measurements along several profiles that was done in 2018 field campaign. So you can see here the wave collection was done in 2 deployments. So we have profiles over the reef and in along the gap in between the reefs at 2 different times, and 1 location offshore where we had constant measurement throughout this. So this was a 1-week field campaign. We took measurements about 3.5 days at each deployment. And so we have some wave data that we can use to validate, to set up and validate an X-Beach hydrodynamic simulation. Now, our base simulation used the bathymetry data that we measured here with our offshore measured heights over this 1-week period in 2018. And we could run the simulation for mean wave height. We could also get other parameters such as water levels, velocities, and braking fractions. And then we could also look at some of the results along several of these profiles where we had our no seagrass or coral input, so nothing special for the bed friction for coral, nor any the vegetation module wasn't set up yet, because we simply needed to get these values for the vegetation. So 1, for the coral, we need to know what value we should be using for bed roughness. For seagrass, we need particularly to know the stem density in several areas. Of course, the extent of seagrass. So when we run the base case without coral or seagrass, of course, we can get good results offshore where we don't have the full impact of the coral and seagrass. But however, when we look in the lagoon, which are these blue lines, then we have overestimation of our wave heights. So in order to narrow down our result, we've tried to use underwater images of the benthic composition to automatically to do image analysis to automatically get values of seagrass density. So at the same time that we were doing bathymetric surveys, we also had a camera pitched on the side of the boat. So on one of these transom mounts here, that's the bathymetric survey pole. The other pole is the camera, and that was taking pictures of the seabed as we went along throughout the day. So we have 4,500 images of seagrass, or at least of the benthic composition. Of those, we had to shortlist images which only had seagrass clearly visible. And then from those images, we can do an image analysis where we take an original image of the seabed. We can do take an average of the background of the image, subtract that from the real image, and then we can highlight the individual leaves of seagrass, as we can see in this middle image. So that's the highlighted image. And then the final step is to trace the edges of each of these seagrass blades that we've identified in the image, and then calculate the stem density and also the thickness of these stems based on the averages in the X and Y direction of each of these images. So this process was done in MATLAB, and we got a very nice relationship between, for example, seagrass density and depth. So of course, in shallower waters, we had higher densities of seagrass than lower depths. And from these values, which are, they range from about 1,600 for very high density patches down to perhaps 200 for very low density patches. So the average value of seagrass density here, at least based on the images, was around 500 leaves per square meter. So we could take the distribution of points of all of our seagrass and classify them into different areas or different patches of seagrass. So we could classify high density patches, medium density or low density patches with 800, 500, and 200 leaves per meter squared. And we use this as input in our XBeach model to highlight areas where we had seagrass. So we've run 2 additional simulations, one where we apply the mean seagrass density in all areas where we have seagrass. A second is applying this high, medium, and low values to specific patches of seagrass, just to see the overall result. So here again, we have an image of the result we had as a base case with no seagrass. And here we have some results where we have the mean seagrass density. Of course, we can see some reduction in the bay here, not so much at the in the more southern end of the bay. It's more discernible in the northern end of the bay. And it really didn't matter that much whether we use the varied N values or mean N values. N here meaning the number of leaves per meter squared, or at least the seagrass density. But what we did find is that we would get approximately around 30% reduction in either case. So the seagrass does contribute quite significantly to the wave reduction in the bay. However, there are still significant local differences. So if we look back at the model result, we can see, for example, on the image to the right, here we can see localized wave height, or at least the average wave height across the simulation. And what we can actually see are some of these streaks behind the reefs, right? Especially in the back of the bay. So when we compare our result with the wave data that we have measured at in the bay, in the upper left-hand plot here, this is offshore, so all the offshore points are quite good. But when we go into the lagoon, for example, at this area at part number 17, then we do see this obvious reduction in wave heights. So the blue line here, it's the original model. The purple line is the measured data. So we have decreased our wave height towards what we have seen in the measurements. However, at other locations, the model results are lower than the measured data. And that's actually because of these patchy results that we have here, which is actually an artifact in the model coming from how our directional spreading is treated. So it means that the surf beat mode of XBeach is very tricky to work with these lagoon environments. I'm pretty sure the results would be a lot better if we were using the non-hydrostatic mode of XBeach. However, that would take an enormous amount of time to compute. So we're still working on improving the result here by working in the hydrostatic mode of XBeach and by resolving some of these directional errors. Now, this talk has only looked at how we have treated the seagrass. Of course, we're also looking at the effects of coral, and that's some work that has been done by Marleen van der Broek, a student in Utrecht, who has worked with YAP. So in fact, both of these projects are working in tandem. We're looking at seagrass, the effect of seagrass, and the effect of coral, and that will be actually presented later on at the Coastal Dynamics next year. So if you come back next year, I will have a much better results to give you. But in the meantime, we still look at answering further research questions. For example, still, what bed roughness can we associate with healthy or dead coral reef? Because in this area, a lot of values that are used in the literature really speak to healthy reefs. But here in this location, there are patches of reef that are not of equivalent health. So that's an open question here. Another is to look at some of these model parameters. So even if we do have them working on a local scale here, how can we upscale this to at least a larger area? So these are just a few research questions that are still ongoing. So that's really the end of my talk. And for information, I have, as I mentioned, I was at Leiden University last year. I've now changed location. So I'm now assistant professor of course of geomorphology at Florida Gulf Coast University in Fort Myers. So if you would need to get in touch with me about this presentation or in general, then please just email me at my new email address. It's cdaly@fgcu.edu. Okay, thank you very much. And I look forward to any questions that you might have.
Yeah, thank you, Chris. It was very interesting, very clear. So there are a few questions. You can maybe take a few minutes to answer some of them.
Yeah.
So please, you can read by yourself, or I can read for you.
Let me. Okay, so I see. Where do my questions start? I think, was it from Andrea? Could you define the measured offshore 2D spectrum offshore of the, or was it? Okay, so I used the offshore, the data from the offshore pressure sensor to input a time series on the model. So you could also do a spectrum, but then if we are trying to compare, actually, yes. Okay, yes. So the data from the offshore wave sensor that was converted into time series of spectral parameters, which were then simulated in XBeach. So at each location, it's actually a time series of spectral parameters that we're looking at. So thank you for that question, Andrea. The next question here is, did you do some calibration of the braking parameter or gamma? No, the default parameters for braking and gamma were used, assuming that we have a very good description of the bathymetry. And in terms of the direction, did I use single dir or multi-dir? It was in the, I think it was the multi-dir mode, but I have to confirm that with you later on. And then this last question, in this paper, they tested a range of seagrass density using SWAN. I used it recently for implementing seagrass. Okay, so it's a link to a paper.
I put that in here earlier, yeah.
Okay, well, thank you so much for sharing that.
I was going to ask what method they use. Is it the Suzuki parameterization? Do you remember what method they use in XBeach?
For the yes, it was. Yes.
Yeah, so they actually found for summer situation in, I think they did in the East Coast, Virginia, they use 400. So it's about the same that you use.
Yeah, so I was very happy that the values that we got from our image analysis were about what you would expect to get in general. So even our upper value of 1600 wasn't exorbitantly high. There could very well be patches of that density. One thing that could be done differently, though, is if we do have such a nice relation between depth and density, instead of making, well, what I've done is to do it in these very large patches. It could be done just simply as a function of depth. And that might actually give a slightly better result, but I don't think we would get anything more than this 30% reduction that we've seen already. The the additional reduction would come from adding or treating the coral as vegetation themselves. So we have also done other surveys where we could look at the 3D morphology of the coral, get the height and somewhat drag coefficients for that. And then adding that, then we have at least a very good representation of what the wave heights are. But still, we have these local spotty results that would still need to be treated.
Well, so I use Suzuki for vegetation, so seagrass, and then reef I do as a Manning's N coefficient. And so I done it in Cayman Islands and Turks and Caicos, and seagrass by far is way more dissipative than reef, at least from my results. So
yes, I think we see that as well here, especially where we have degraded reefs.
Yeah,
it's the seagrass that picks up or takes over from the reef in terms of the controlling the wave heights in the lagoon. Yeah.
Okay. So, Chris, you have 2 more questions. If you scroll up your the chat, maybe you can answer directly in the chat. And so we go on with the last presentation for today. So, Juan, I leave you present.
Okay. Can you see?
Yes.
So I'm probably lessons learned, because it's gonna be mostly descriptive of the behavior I saw from the model, testing different, doing different things to the model, including resolution and the values of viscosity, horizontal viscosity. This is kind of what I showed in January, just because after that I did some changes in the model, and I just it just went downhill from there. But so what I was trying to do was to implement the 4D vara simulation into ROMs. There's a H-shaped radar network in Puerto Rico, so the idea was to assimilate H-shaped radar into ROMs and also the buoys that are available. So when I started reading about how to do the assimilation, turns out it's very important to have the correct mean and variance of the state variables and normalization factors. So this was kind of a big obstacle right away, because this means that the model will have to be run with like a baseline configuration, for at least 1 year or more. So that will require the model to be stable, and also to get, if the mean and variances of the baseline model are too off, then it will not, it will affect how the assimilation works, because it has to do at some point, has to kind of do like a least squares difference, between what you are putting as the simulation and the model results. So if the model is way off, and particularly we had found before, the eddies will be like rotating in the wrong direction, for example, then it will be extremely difficult to get any kind of assimilation. So I did a bunch of testing with viscosity and boundaries. I did a lot of testing of all these variables, trying to get the model to run at least for 6 months. And then initially I did from December 1st, 2017 to April 1st, 2018. In this case, I was using RTOS for the boundary. And again, as I will show later the effects of the viscosity. But one of the problems was that the model and the boundaries will be stable, say when the viscosity was 50, but then you put it to 25, and then I will have to do some kind of smoothing in the boundary or some smoothing in the fields to get it to be stable. So it was an extremely time-consuming process. And also another thing I had to do was because this is kind of the main thing that I wanted to just show and for discussion and for just learning in general about modeling in this area. So initially the model domain was up to 17.5 north. And then I quickly realized, especially when I start getting to lower viscosities, this area here, it's very, very dynamic in terms of the eddies that come from the southeast. We have the shelf here. So then there's a lot of interactions here and a lot of like eddy shedding, and sometimes you get jets. And turns out that that boundary was right at where that dynamics change. So that led me to make a larger domain. But then you will see, I will show the larger domain, but so you have an idea, the Dominican Republic is here. So there's a lot of tidal action here. So I didn't want it to make too big of a domain. So I extended it a bit here, but not quite getting to the Dominican Republic, because then I will have a lot of masking issues in the boundary. And ROMS doesn't really do well with any kind of masking on the boundary. So it's extremely tricky to get a domain that is not huge but able to deal with all the of the obstacles. So that was another challenge I found. But if anyone this will also have implications, because I thought it would be nice to do a nest here. But there's so many dynamics happening everywhere where you put any nesting domain that it's just dealing with the boundaries. It's a pretty big challenge. This was like the last slides that I showed in January. These were the new vertical levels that I wanted to test. And this is around 67, so this is like in the southwest. And you can see here how abrupt the shelf is. So I was like, oh, I'm gonna run this immediately. I run, the model blew up. So this kind of vertical, this is a sigma level model, terrain following, but it has a parameter where you kind of control so that the top layers are more horizontal, and then you can control how the bottom influences through the mid-water. But these things immediately made the model unstable. And this led to an extraordinary amount of work of redoing the grid and smoothing and retesting. Another thing that was very troublesome is like this is right at the shelf. So this is what I was trying to test initially. The model definitely doesn't like this. And then later I start plotting where the actual points are, in the grid, and it will be, a point here, and then the next point will be here. So this is, pretty much artificial anyway. So a lot of details that, they keep piling up. So this is what this was the initial or the old version of the model. So you can see it finished at 17.4 north, and this is the vertical distribution that it had. So I added 2 more vertical levels, and I increased the extent of the domain north and south and east and west too. But this gives you again an idea of why I really don't like this terrain following coordinates. Like I don't think there's I played a lot with the parameters, and it's I think it would be, I don't even know if it's possible to do the kind of distribution that I would prefer, because I don't think, especially when you look at the dynamics and the values from the model, like there's no way that this bump here should influence, all the way up to 1 kilometer deep. Like this is not like a accurate representation of how the fields behave. So that's why I ask about how the NEMO model, what kind of options it has, because I think it will be interesting to try another model for this kind of region. And you can see this all these small, oscillations here in the vertical levels. They definitely cause instability. And this is what I ended up with. This was the initial original version. I didn't like that it was too smooth because that's really not how the shelf looks in the area. So I did a lot of work, and I mean, this is a more accurate representation. It's shallow, and then it deepens a bit, and then the shelf is a bit shallower than in between. And here you can see the distribution of the vertical points. But still, there's this these weird transitions here that they really don't. Like these levels don't agree with, for example, how the temperature and salinity behave. And this is more in detail. This is a table of how I changed, the model, the definition of the grid. So it's much larger on the east-west direction. I mean north-south. I also increased the resolution from 1 kilometer to 1.5 in order to not increase the grid size too much. But even then, that's what ended up happening. And I even increasing 4 vertical levels, and this doesn't seem like much of a difference. But when you multiply it, since it's 3D, it ended up going up to like 3.2 million points versus 2.2 million before. And I was doing long simulations, and then it would take forever because I was doing before, like I think I was doing 1 day in 1 hour of computing, then it turned out to be 1 day in almost 1.6 hours. So it just kept getting worse. And this is the geographical extent of the older model. So it cut right there and then very close to Mona Island. So I extended it, but now I kind of want to redo this again and have a larger domain, because the TPXO is not really that good for this area in between Puerto Rico and the Dominican Republic, and especially for you have to put the U and V velocities from a tidal model, and I don't think TPXO is doing that correctly there. This is some figures of the sensitivity. Again, it just shows how much of a different solution you can get just by changing viscosity. And again, we have a buoy here. At least we have radar, so we have a good idea what's happening around here. But anywhere else, it's like you do 5 different horizontal viscosities. Who knows what's the real one? So since I was doing for a simulation, my main goal was to at least have a accurate representation of the features. So for example, make sure that the eddies were, in the right size of kilometers and things like that. So with 100, a value of 100 meters squared per second, there's an eddy here, but you can see it's pretty smooth elsewhere, only like fairly larger features. And this is the same date, so it's all for 14th of December, 2017. So I switch it down to 50 meters squared per second, and starts to look more alive. You have an eddy here, you have a more representative jet here from the tides. You have some more action in between the islands. But again, it looks like a completely different model, and it's the same date. And then if I go down to, this was 25 meters squared per second, completely different solution. I go down to 15. This one looks, the more, you say, okay, this looks realistic because there's conveyor belt here. You have a lot of action in between the islands. But again, it's same date, same hour, completely different result. So if you don't have, as it is, there's not enough data. You have radar here, but we don't have a radar here. We don't have a radar in between here. So, if you're doing like larvae distribution, things like that, you do this or you do this, the larvae will end up different than what's the reality. So, and those sensitivities, these were done with the previous grid version. And then I will eventually the model will blow up, especially here, because you have all these eddies, and then you're putting the eddy through the boundary condition, and it just gets unstable. These are results then for the new grid that I did, and just so you have an idea of how much it changes in terms of the of the input that you can put in the model. Initially, the other grid will be cut off around here at 17.5. And you can see it's very, very dynamic area all over. So that's what was being put into the boundary initially, and there was obviously too much energy to deal with. So now it goes down to, I think it's like 16 north. So now there's more of a relaxation area between the boundary and where the interaction with the shell happens. But even then, you see there's eddies here. This is kind of what right now is the problem with the configuration. It's not properly solving what's happening in the MONA channel. So there's this kind of reverse current. Kind of what happens is you have some circulation that goes to the boundary, and then it just circulates around it, and then it gets thrown back to Puerto Rico, and this is not really what's happening. So because we have the radar, so now that's the problem to fix. I will say, to get this west area of the domain working properly, because it's just too much of a strong current, and then it just overtakes to whatever will be happening here. And this is some validation with the HF radar. This is kind of the other problem. It's sometimes the HF radar is spotty, so it's very difficult to precisely select a date for validation. But then with the new configuration, the model was taking just too long, and I would have fix something, and then I would have to wait like 3 days, and it just became extremely difficult to deal with. But you can see that at least representatively, because the idea was to put this the HF radar into assimilating into ROM. So ROM didn't have to be perfect, but at least you can see like here, this is the same scale. So kind of the same velocity, is kind of a similar, direction of the flow. But then here on the other side of MONA, or no, this is another small MONA is here. You can see there's quite a bit of a difference here. So this is for another date. Again, you see this current flowing towards the east on the southwest of Puerto Rico. It's not there in the radar. And there's kind of some, similitude here in this area. But again, here it doesn't look much at all. So I think that I still have to clean up, put away the boundaries even farther away, because there's just too much energy to moving around. And this really shows that jet completely overtaking the circulation. So then the problem is that in terms of ROMs, you have this extremely fast current here, which is really not a reality, but then it starts generating these circulation centers that are, obviously are not going to exist, because they are just responding to this artificial current. So that's what I wanted to show, and hopefully this helps other people, and kind of how to at least conceptually design these models. And definitely the issue of the boundaries is it's very, we have whatever models are out there, but like they showed previously, if the global model is not even doing, the circulation that comes from Brazil is not correct, then we have little hope that it will be like, nowhere to where it should be, near to the island.
Okay, thank you, Juan. Thank you very much. So I don't know if there are some questions. There is maybe by Bruno. Okay, discussion on maybe on ROMs on the Northeast Pacific.
Let me see, ocean cleanup. Okay, yeah, sounds good. Turbulence model, I don't remember right now. I think it's the KE. I will have to look into that. And increase of the spurious. No, yeah. So that's precisely the what I noticed. The problems are not internally. It like comes from the boundaries. Yeah. And so for the newer version, I'm using HiCom because there's no archive of RTOP, so I didn't have the boundaries for 2022, so I had to use HiCom. I could look into using the Copernicus. I work with the Copernicus model for a model in the Baltic Sea, and it worked perfectly. So yeah, I was kind of in a hurry, so I just used HiCom, but definitely I can look into using the Copernicus. Yeah. Thanks for the recommendation.
This is a remark from Julie. So thanks, Juan, for your honest presentation. So what do you think about?
The boundaries for 3D, 2D, I'm using HiCom and RTOS. Yeah.
It was a remark on the difficulty on tuning ocean models. Yeah, so definitely, yes, I think we have seen that it's quite a big task.
Yeah, and then you fix something, and these things are completely non-linear. So you just keep fixing and fixing.
Yeah. So we enter the final part of our workshop. So we are supposed to discuss about these topics. So we can continue answering the questions that may arise during these last minutes. Just maybe remind that most of the product, the simulation results will be available in the website of CARIB-COAST. You will have some database results. You will have a result that you can exploit to maybe to use as boundary condition for your own simulations. And that's it. I don't know if the coordinator of the project want to add something else. Otherwise, we can simply see if there are many more questions on what have been presented. And of course, we thank all the participants and the people that present. Okay, so in case there's nothing to add, we can, okay, it's maybe, we will make the video available for those who missed something. Okay, so yeah, everything has been registered and will be diffused in the same web platform in the CARIB-COAST site. So, okay, nice. Then we can maybe end here. So thank you to everyone again. And
for the team of CARIB-COAST, see you tomorrow.
Yes.
Thank you for the presentation, for the other people who assist at this workshop.